we've just come across an example with that cart pole thing, where we've ended up with a non-linear equation. And everything we've done in this module so far has relied on the fact that we're using linear algebra, linear mathematics. The whole world is nice and linear. So I'm just going to very, very briefly discuss with you non-linearity, problems with time, and other ways of doing things. Okay, just an introduction. We might come back and look at the other ways of doing things in a week or two, but let's look at the real world issues. So we've got non-linearity, and the second one is this problem with time. Have you come across sampled data before, or sampled systems? Maybe not. Okay, we'll come on to that. So let's do the easy bit first, because this is quite easy to grasp, and it ties in with maybe a number of other things that you've done with similar methods. What we've been working with have been transfer functions. And right from the first week, I've been standing here saying transfer functions, transfer functions, transfer functions. Okay, they've got limitations. Fundamentally, what a transfer function is, it's a high-order differential equation expressed typically in the Laplace domain as some coefficients of s on top of each other. The trouble with a transfer function is that it can only ever relate one input to one output. Okay, so if you're looking at a system with multiple things going on, you need multiple transfer functions. So that's not tremendously helpful. So if we take our high-order differential equation, instead of having one, let's say, third-order differential equation, third-order system, big nasty transfer function with s cubed in it, can I represent that third-order differential equation as three first-order equations? Three separate first-order equations. Okay. The answer is yes, I can. And if we do that, we can present these first-order equations in the matrix format. Okay, it's a little bit like what we did in dynamics, where we expanded into multiple degrees of freedom by having lots of simple equations instead of having one complicated one. And that's the format. Okay. X are the variables. Now for this type of modelling, it's really quite interesting because we're not tied to one input on one output. I can decide entirely for myself what variables I choose to be in there. Okay, and they're referred to as the state variables. They're not necessarily the inputs or the outputs of the system. They're just some variables within the system. And the nature of the equations is always first order differential. So for example, x1 dot is some coefficients times the state variables plus possibly something times the input. Okay, and those are the state equations. They don't make sense yet because I need to relate those to the outputs. So I need a second set of equations, which are these things, where y of t is the output, is some bunch of coefficients times the state variables plus possibly something to do directly with the input. Quite often the D matrix is naught. Okay. So that's a third order system described as three first order equations. And that representation, that type of modelling, transfer function is one way of doing things. The other approach is known as state space or state space modelling. Okay, and I think that you guys have been introduced to state space by Rob in Maths 2 last year, or the year before, or whenever you did it. I think you've had an introduction to that. Okay, and it's a very powerful tool in control. The reason it's a powerful tool is because we get to choose what we like to set up the equations. I can expand u of t, that's a scalar quantity at the minute. I can expand that into a vector quantity, so I can look at the behaviour of a system in response to multiple inputs. Okay, so I can have more than one input into the system simultaneously. I can also expand this expression, so I can have multiple outputs. Okay, and the whole thing relates about understanding what's happening to these state variables. And then there's a whole bunch of clever control algorithms you can make up just by stealing the state variable information, but that's not for this module. Okay. Very roughly, what we've been looking at with transfer functions is referred to as classical control. If you move into using state space representation, you're moving into what is called modern control. You won't think it's modern, it's been around for about 30 years. But that's the distinction. What generally we've been looking at so far is what's called classical control. There's an example. You've seen it before. I'm going to choose some state variables, things that suit me. One state variable is displacement, the other state variable is x. There's my differential equation, inertia plus damping plus spring. I can express that in terms of the state variables. Okay. x2 dot, rearrange around that, gives me one equation, and x1 dot, well, that's just equal to x2. Okay, so that matrix form, representing that as a set of state equations, it looks like that. The output in this case is 1 times x1. Which I can't remember what it was. That was velocity, I think, wasn't it? No, that's position, sorry. So that's the kind of shape they take. We may come back to it in a week or two for a bit of time, but you need to be aware of these state space techniques. Don't know what's happened to the animations on these slides. They've gone backwards. And you can easily expand all this lot to deal with higher order systems. There's a third order one with multiple inputs and multiple outputs. You see you've got 2 inputs here, 2 outputs there. Easily expanded. Okay, so we need to be aware of that. Not going to do much with it, but that's the way ahead if you want to do more complex things. The other thing I want to very briefly mention is time. Now, in most cases, probably including what's inside that, there's a control algorithm inside that, just keeping me upright. How do you think it's implemented? What's inside there? Is it a big clockwork mechanism or something? What's actually running that control algorithm, do you think? Small Arduino, somebody said. The gyroscope's just a sensor, really, isn't it? You can use them for feedback, but what the answer I was after, to be honest, is some kind of processing device onto which you can upload the algorithm. Yeah? So it's quite likely that inside that there's fundamentally a microcomputer, a microprocessor. Everything we've done so far has been to do with differential equations. Okay? And differential equations, how far back do I need to send you out? Like A-level maths, a lot of you have got. When you first got introduced to differentiation, when does delta x by delta t become dt, dx by dt? Is when the delta t term becomes infinitely small, isn't it? When it trends to 0. If you go right back to the definition of a differential, it's when dt or delta t becomes infinitely small. If you've got a digital system, like any sort of computing device generally, delta t cannot approach 0 because of the way they work. Okay. If you had a computer looking at a piece of equipment in the laboratory and you're trying to measure temperature, it's not a continuous process. Okay, it's a sampled process. It'll go and have a look at the information coming in, decide where to put that number, go and put it somewhere, maybe put it on the screen for you to see, then it'll go back and say, oh, I better look again. And it will check the reality again. And because of the sequential nature of a digital process like that, there is a time space between each real data point. Okay? They operate in what we call discrete time. Or you might refer to them, you hear them referred to as a sampled data system, because all they can do is sample data at intervals in time. They can't do differentiation, because they can't get delta t down to 0. Okay. So differential equations become redundant. They don't fit. You can make delta t smaller and smaller and smaller by certain methods. Okay. Gentleman maybe who's got his head in Arduinos and digital devices, what do you need to do to computer to increase the rate of sampling, do you think? It's a very crude answer. You throw money at it and you buy faster hardware, but you will never get it to a point where it's continuous. It's still discrete time. Differential equations don't work anymore. So you need a brand new sort of mathematics. That's the bad news. The good news is it's much easier than differential equations. And when you're operating in discrete or sampled time, what we have to do is describe things in terms of difference equations rather than differential equations. Okay. So you might choose to approximate a differential by the value of my variable this time minus the value last time divided by my sample interval, rather than saying dy by dt. It's y this time minus y that last time divided by the time interval, and you get an average gradient, don't you? That's what we have to do if we're working in the discrete time domain. We have to take all the differential equations and turn them into difference equations, which are basically just adding up and subtracting. We do introduce a different operator. You're used to using the Laplace operator. Now we introduce a different called the Z operator, and all the Z operator means is a gap of one interval. So if you've got a number and Z times that number is the number last time. Z squared is the number the time before that. Okay, so it's all based on discrete samples of time. Of course, when you connect your digital machine back to the real world, you need to reconstruct time, because you've got information at discrete events. How do you fill in the gaps? Okay, and there's all sorts of ways to do that. The simplest is just to let this number last until the next one comes along. But you end up with quite messy data that way. Again, it's more for you to think about than to... I won't be asking you any hard sums questions about it. The last bit is what we just came across in that example. Okay, it's all to do with nonlinearity. You know by now, you've been studying engineering long enough, that the real world is not a linear place. So we need to learn to deal with nonlinearities. Okay, there's lots and lots of techniques to do this, but a good proportion of them fundamentally boil around how can I fiddle it so it looks linear. Okay. I'm sure it's not described that way, but that's what a lot of these techniques are. Finding ways to pretend, or finding ways to allow us to apply our linear technologies. The first one, I guess, is what I call piecewise linearization. And we've done a little bit of that already. If I had a function that is non-linear, I don't know. something like that. And this is particularly appropriate in control, because in lots of control what we're trying to do is to get something to stay at a fixed value. And what we do with piecewise linearization, let's say I want to control that about a particular value of x. I would design all of my control stuff as if it was linear, with that gradient in the middle. If I wanted to operate the same system at a different place, I would pretend it's linear either side of that spot. Okay. So fundamentally what I'm doing is I'm breaking up that smooth non-linear behavior into a sequence of straight line pieces. Okay, and arranging my controller to recognize where it is and which straight line it should be calculating from. Piecewise linearization. That's a little bit like what the standard mathematical thing for the sines and cosine is. Okay, now let's do the cosine. It's easier to explain that one way. There's a cosine, I think. If you remember the assumptions that we made not that long ago, what we said is that for small angles of theta, cosine equals 1. So what I've done really is I've done a piecewise linearization, which is to say that next to theta equals 0, that's just linear value. And the further that I go away from that place around which I've linearized, the less accurate it gets. Same we did for the sinusoid. In regions near 0, sine theta is about the same as theta, so long as you're using radians. Okay. It's nowhere near true over here, is it? So what we've done in that case, and you've been doing it for years by now, is a very small piece of piecewise linearization by saying, so long as I'm near a fixed point, I'm going to make some assumptions. Yeah. Does that make sense? You've done that. You may not have realized it. I happen to know for a fact is that's how they arrange the fueling controllers in Rolls-Royce gas turbine engines. Okay, because one of my ex-students used to design them. He said, "Oh yeah, we do this." I thought, okay, so it's actually used in really quite complex and difficult and technologically highly advanced things. It's still okay to do piecewise linearization as long as you do it properly. And in that particular case, it was only necessary to get the engine through the transients up to its normal operating condition, around which we kind of understand everything. Done that one, tick. What else can we do? Well, these things called describing functions are interesting. You can't do piecewise linearization on all nonlinearities. That's a nonlinear behavior. It's what I would call a smooth nonlinearity. That's a nonlinear behavior, but it's what I would call a discontinuous nonlinearity because it's got a corner in it. Okay. And no matter how much I try and kid you otherwise, it's really difficult to do piecewise linearization around a corner. Okay, you can do it with nice smoothly changing things where you get discontinuous nonlinearities, and that's a relatively benign one. Let's put a nastier one up. Okay, there's a discontinuous nonlinearity. If the input is negative, you get minus something. If the input is positive, you get plus something. You try linearizing that around a value of 0. Okay, so it's a mess. So there are other techniques we use when we've got things like this, which include things like describing functions. Okay. And some of these are graphical techniques where you almost take a picture of the system in that condition and take a picture of the system in that condition. With a pair of scissors that represent your control decisions, you match the two halves together. So it does something useful. And there's all sorts of other stuff. There are mathematical techniques for checking for stability in non-linear systems and so forth as well. I'm not going to go into any detail about any of them, but moving ahead from this module, that's the kind of stuff you need to be aware of. Yeah, that's the next stage of complexity after the relatively straightforward stuff that we've been doing.